Exponential models is another way to say applications or word problems for exponential functions. The half-life means that after 5,730 years, however much carbon-14 was present at the beginning, only half of it will remain after that many years. So suppose a sample began with 100 grams. So start with 100. And if the half-life is 5,730 years, we could say, all right, I'm going to use an exponential growth model So we start with the beginning amount and then the exponential function, with r being the rate and t being the time in years. If r is positive, this 100 is going to grow bigger and bigger and bigger. With this one, half means that it's actually getting smaller, and so this r is going to be negative. The next thing we need to do is find out how much is r. Well, that's going to involve the word half in this many years. So this 100 grams is going to be cut in half. In other words, the amount will be 50 after 5,730 years. And now we need to solve for r. The first thing to do is divide both sides by 100. So that's going to be 50 divided by 100, or if you reduce it, 1/2. And now to solve for r, we need to eliminate the e. So use the opposite, which is the natural log function. Take the natural log of both sides. And then natural log and e are going to eliminate each other or cancel each other out. And so we'll have just r times 5730 equals the natural log of 1/2. And it's best to not get a decimal approximation right here. Just do the algebra with that natural log 1/2, and at the end type everything into the calculator. So the next thing to do is divide by 5730. So we'll have the natural log of 1/2, which gets divided by 5730. And that should turn out to be a negative number, because this thing is shrinking, so the rate, which is the growth rate, should be negative. So the natural log of 1/2 parentheses gets divided by 5730. And yes, it's negative. In fact, r equals negative. The decimal needs to be moved over to the left 4 places, so that's going to be 3 zeros and then a 1, 2, 1. Alright, now on to the second part. How much of the sample would remain after 20,000 years? So we now have the amount is equal to a 100, the e, so I'm now going back to this and using r as negative 0.000121, and then the time is 20,000 years. Alright, put that in the calculator and we've got it. So the original 100 and then e to the negative 0.000121 times 20,000, and the amount that's left is only 8.892, and the units are grams. So there's a little less than 9 grams left out of the 100.